Okay guys, in the last video we calculate the rate of change of momentum, which is given by this relation. I call it, let's say, equation number 1. By definition, we know that rate of change of momentum is equal to the force. By definition, we know that rate of change of momentum is equal to the force. We can say that force is equal to delta P over delta T. If we have momentum along x-axis, then the force will be along x-axis. I represent it by Fx. Now Fx is equal to delta Px over delta T. Value is here, so I will put it mvx square over L. This is, let's say, equation number 2. Now this is the force exerted by a molecule on the wall, but the wall is perpendicular to x-axis because we have this one. This is the force exerted by the molecule, this molecule on this wall, and this wall is perpendicular to x-axis. On the wall, which is perpendicular to x-axis. Now this was the force exerted by a single molecule. We suppose that there are n molecules in the container. We suppose that there are n molecules in the container. Then the force exerted on the wall due to n molecules will be equal to, I call it Fx, okay, which will be equal to force exerted by the first molecule plus force exerted by second molecule plus force exerted by third molecule plus up to force exerted by nth molecule on this one. So I put a summation sign here. This is the sum of forces exerted by all the molecules on which wall? On this wall, which is perpendicular to the x-axis. So it means that the force exerted by first molecule, so its velocity will be, its mass will be m1, okay, and its velocity will be v1 of x divided by L square. But here we consider the molecule of a single of the same gases, so their masses will be the same. Like the masses of all the molecule will be the same. So m mass of the first molecule times velocity might be different divided by length square plus m v2x over L square. L, sorry, this is L. This is square plus mv3x square over L plus up to mv nx square divided by L. So here on this side we have this mass and L. They are common in every term, so I will keep it outside. So we have m over L. We have m over L is common. So here we left with v1x square plus v2x square plus up to vnx square. This is the force exerted on the wall due to n molecules, but the wall is perpendicular to x-axis. Now next, we know that the area of this wall A, B, C, D will be, so here we have this area. The area of this wall A, B, C, D, the area of wall A, B, C, D is L square, because we have this length is L, this length is also L, because we have a cube, so every side is the same length, L, 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 L. So the area of this wall is L square. What it means? It means that if this is the area of this wall, then the pressure is defined as how we can define the pressure. Pressure is defined as force per unit area. So the pressure exerted on the wall A, B, C, D, on this wall will be is P, which is equal to force exerted by the molecules per unit area. We can say that pressure will be equal to force exerted by n molecules on this wall divided by area, which is L square. Now using the way equation, I call it equation number 3, yes. So using equation 3, and I call this is equation number 4. Using equation 3 and 4, we have, if I put equation 3 and equation 4, then we have the pressure value, which is P, which is equal to, instead of this term I will put this one, which is M over L V1x square plus V2x square plus up to Vnx square divided by L square. I can say that this is equal to P is equal to M over L cube V1x square plus V2x square plus up to plus Vnx square. This is, let's say, equation number 5. So this is the value of the pressure, but we have to calculate the mass, which is unknown here. So for that we use the concept of density. We know that density rho, which is equal to mass per unit, total mass divided by total volume. Now we have n molecules and each molecule has a mass m, so the total mass will be nm. And we have a cube and each side of the cube has a length L, okay, so its volume will be L cube. So instead of this rho I will put n into m divided by L cube. If I calculate the value of mass here, which is m, which is equal to rho L cube over n, where rho is the density, okay. Now if I put this value here, which I call it equation number 6, and equation number 5 using equation 6 and 5, we have P is equal to, instead of mass, I will put this rho L square over N into V1x square plus V2x square plus up to Vnx square divided by, we have L cube. This is also L cube, yes, sorry. So this is also L cube. Now this L cube will cancel with this L cube. So we have the value of pressure, which is now equal to rho into V1x square plus V2x square plus up to Vnx square over N. Now we got this relation, which I will write it here again, like P is equal to rho into V1x square plus V2x square plus up to Vnx square over N, where N is the total number of particles. Now normally we define the average value as, or the average velocity as, the sum of all the velocity divided by the total number. Like average velocity is velocity of first particle plus velocity of second particle plus up to velocity of nth particle divided by n. This will give us the average velocity. Now this is the average velocity. Now if I take square of this velocity and then I divide it by n, then we got it mean square velocity. We call it mean square velocity. Like this is mean, without square we have the mean or average. But if I take square and then divide by n, we got mean square velocity. And we represent this mean square velocity by this V1x square plus V2x square plus up to plus Vnx square divided by n. This is the mean square velocity. This is mean square velocity, and we represent it by this symbol, either Vx square with a bar above it, or we simply represent it by Vx square. So this will give us the mean square velocity. So here I will replace this term by this one, so it will give us the mean square velocity. So we have the pressure, which is rho into Vx square. You can write it as like this, rho into Vx square with a bar here. So both the notations give us the same meaning. So overall we can say that P is equal to rho into Vx square. This is, let's say, equation number 7, because this was equation number 6. So here we have equation number 7 is this one. Now, as I already mentioned before, that we have the velocity which has 3 components. One is Vx, which is along x-axis, one is Vy, which is along y-axis, and one is Vz, which is along z-axis. So the velocity has 3 components, so the velocity can be written in component wise like this: Vx, which is along x-axis, plus Vy, which is along y-axis, plus Vz, which is along z-axis. So if I take the square, by square I means V dot V, we get V square, which is equal to Vx square plus Vy square plus Vz square. So if I take the average velocity, then it will be equal to, we can apply it separately to each component. So we have Vx square mean plus mean square velocity along y-axis plus mean square velocity along z-axis. So this is the total velocity. So if I take this mean, then we have to apply the mean to everyone, to each component. Now we assume that the velocity along x-axis, along y-axis and along z-axis is the same. We assume that the velocity of molecule along x-axis will be equal to velocity of molecule along y-axis, which will be equal to velocity of molecule along z-axis. So this implies that Vx square velocity along mean square velocity along x-axis will be equal to mean square velocity along y-axis, which will be equal to mean square velocity along z-axis. So if I put all this value here, I can say that in this equation, then we have V square, mean square velocity will be equal to mean square velocity along x-axis plus mean square velocity along y-axis, which is, I replace by Vx square, mean square velocity along x-axis plus mean square velocity along z-axis. So I replace it by Vx square, because these velocity are the same. So it means that V square, a mean square velocity, will be equal to 3 times mean square velocity Vx square. So using this value, this is equation, let's say 8, using equation 8 and 7. So we have the pressure value, which is Vx square. So if I calculate the value of Vx square, so this will be equal to 1 over 3 V square. So we have 1 over 3 rho into V square. So this is the final result. The final result is pressure is equal to 1 over 3 rho into V square. Now Pascal law states that fluid exert equal force in all directions. Now this is the pressure exerted by the molecule on x-axis. So according to Pascal law, fluid exert equal force in all directions. So the value of pressure on walls of the container will be on every wall of the container will be 1 over 3 rho into V square. Now if I calculate the value of this mean square velocity, then mean square velocity will be equal to 3p over rho. Now if I take the square root of both this side, now inside this square root we have, this is the mean square velocity. If I take the square root, we call it root mean square. So root mean square root, mean ms means mean square. So we have the square root. So for this I use this subscript, in the subscript this symbol r, and we have, this is the mean square, so I use this ms. So it tells us root mean square velocity, which is 3p over rho square. So here this term represent the root mean square velocity. So we already calculate the pressure. in terms of mean square velocity, and we also calculate the root mean square velocity in terms of pressure and density. So this is all about kinetic theory of pressure on the basis of kinetic theory of gases.